Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the Miller cycle and the optimizations. Alternative to lowering the compression ratio and simultaneously increasing the expansion ratio of an Otto or diesel cycle is to lower compression ratio only while the expansion ratio is kept as the original. Miller proposed a cycle which has the following characteristics. 1. Effective compression stroke is shorter than expansion stroke. 2. Increased charging pressure. 3. Variable valve timing. Miller proposed the use of early intake valve closing to provide internal cooling before compression so as to reduce compressing work. Miller further proposed increasing the burst pressure to compensate for the reduced inlet duration. By proper selection of burst pressure and variation of intake valve closing time, Miller showed that turbocharged engines could maintain sea-level power while operating over varying altitudes. A modified Otto cycle is known as a Miller Otto cycle, whose PV and TS diagrams are shown in figures 10.17 and 10.18. Also, by applying the idea of intake supercharging of the Atkinson cycle, the Otto cycle can be updated to the Miller Otto cycle. A modified dual cycle is known as a Miller dual cycle, whose PV and TS diagrams are shown in figures 10.19 and 10.20. Also, by applying the idea of intake supercharge of the Atkinson cycle, the dual cycle can be updated to the Miller dual cycle. A modified diesel cycle is known as the Miller diesel cycle, whose PV and TS diagrams are shown in figures 10.21 and 10.22. Also, by applying the idea of intake supercharged of the Atkinson cycle, the diesel cycle can be updated to the Miller diesel cycle. The thermal efficiencies are found increasing with the compression ratios operating in the temperature limits T1 and T3, and the limitation is the Carnot efficiency. While the cyclic specific network increases with the compression ratio, reaches a maximum, and then starts to decrease as shown in the figure. With less work output per cycle, a larger mass flow rate is needed to maintain the same expected power output, which may not be economical, especially for the vehicles. Therefore, there should be a compromise between the thermal efficiency and the network output. The optimizations for the Miller cycles can be done following the idea presented former. Here, the relatively simple Miller Otto cycle among Miller cycles is taken as an example to show the procedure. The temperature for each state can be determined based on state 1 and the process. For the isentropic compression process, state 1 to state 2, we have this relation. The other temperatures can be determined by definition. For the heat addition from the isochoric process, state 2 to state 3, we have this relation. The heat rejections from the isochoric and the isobaric process, state 4 to state B to state 1, we have this relation. The thermal efficiency of the Miller-Otto cycle, by definition, is expressed as equation 1040. We are now trying to determine the optimal compression ratio at which the cyclic specific network reaches maximum. By definition, the specific cycle network is substituting the state temperatures and following the ways having been used before. The derivatives are, we can find there exists indeed maximum specific cycle network. Setting the first order derivative to 0, we have the end compression temperature and the optimum compression ratio. The maximum dimensionless cyclic specific network is the optimum thermal efficiency is the optimum mean effective pressure. Again, questions for you. Can you try to find the compression ratio for the maximum MEP? Is it the same as that for the maximum cyclic specific network? Okay, that's all for this task. Thank you very much and see you next time.